All right, so let's continue with a couple of examples. Sorry about the phone. I'm not gonna. I didn't think about actually making another video just because of that, because it happened at the end of the video. So let's, like I said, let's go over a couple of examples on how to compute this Legendre series, because that's basically the heaviest part of the work when you move on to boundary value problems. If you look on the formula sheet, there are actually two formulas, the so-called recurrence formulas that you can use repeatedly. And so let's write them down here. One of them is, let's say it's n plus 1 Pn plus 1 of x plus n Pn minus 1 of x equals 2n plus 1 x Pn of x. And I'm going to rewrite this one because in practice you will see you're going to use it from right to left when you have x Pn of x in the integral, or x to another certain power times Pn of x. So I'm going to divide by 2n plus 1. I mean, it's given like that because it's easier to, it's more compact without fractions. But in practice, you will see typically what you want is to get everything in terms of polynomials. So I mean, you basically replace x times Pn of x in terms of summation of, or linear combination of other polynomials. So xPn is, if I divide by 2n plus 1, that's n plus 1 over 2n plus 1 p sub n plus 1 of x plus n over 2n plus 1 pn minus 1 of x. Things will get a little bit tedious pretty quickly, as you'll see. Not the worst of the worlds, but still something to practice, you know, before you move on with, before you go faster, right? And another very important recurrence relation is Pn plus 1 prime of x, so the derivative of this, minus Pn minus 1 prime of x is equal to 2n plus 1 Pn of x. And in practice, again, you will actually write Pn in terms of this, because your goal is to integrate Pn when you compute this Legendre series. So you could think of this giving you an antiderivative for Pn. So I'm going to rewrite this as Pn of x equals 1 over 2n plus 1 Pn plus 1 prime of x minus 1 over 2n plus 1 p prime n minus 1 of x. All right, so let's focus on these two relations and see how they play out. Another important aspect to keep in mind, we discussed this last time, right? I mean, in earlier lectures. The coefficients of the Legendre polynomials are in such a way that Pn of 1 equals 1, no matter what n is, whether it's even or odd. Furthermore, P2n plus 1 of 0 is 0. That's easy to understand, right? I mean, because the even, the odd polynomials contain terms like a1x, a3x squared. So all of them have x as a factor. So if I replace x with 0, then the odd polynomial at 0 will always be 0. Whereas if you plug in 0 into the even polynomial, this is going to be a naught, which we proved in the homework. That's equal to, the more compact form is minus 1 to the n 2n factorial over 2 to the power 2n n factorial squared. Now I should say that most of the time we're going to be happy to leave the answer in terms of even polynomials evaluated at 0, especially if there's lots of them in the final answer, because if you replace them with the corresponding factorial, it gets tedious rather quickly. In one example, I'm going to do that replacement, but unless otherwise specified, you will be happy to leave the answer in this format. P some even power of 0. Now, if it's odd power, you replace it with 0, obviously, but, or if it's 1, it's replaced by 1. But you can leave it like that, P to n of 0, and you don't have to replace it with the corresponding value of that constant in terms of these factorials. Okay, so let's go over a couple of examples of computing Legendre series. So let's start with the easy one, right? So let's find the odd and even Legendre series of the constant function 1. So you just take 1 as a function of x. Okay, so let's start with the even one. So I want 1 in the form of a summation of a to n p to n of x. Then according to the formula, a to n is the integral, and the interval, by the way, is 0, 1, right? So a to n, look back to the formula for the even Legendre series. It's going to be 4n plus 1, and the integral from 0 to 1, 1 times p to n of x. All right, so pay attention to my recurrence relation now. This is the part when it's going to be tedious and you have to practice a little bit and go slow in the beginning. I'm going to have to write p to n in terms of derivatives because the goal is to integrate this. So I'm going to simply plug in n to n for n everywhere in the formula here, right? The formula is given for a given n. You have p to n of x in your notation. So everywhere here, I'm going to replace n with 2n. So let's look carefully. We have 4n plus 1, 1 over 2 times 2n plus 2n, quantity 2n, plus 1, p prime 2n plus 1 of x, minus 1 over 2 times 2n, plus 1, p prime 2n minus 1 of x, dx. All right, so the coefficient on the outside, we can factor it out. We could have actually factored it out from here, basically, because it's the same in this case. And the antiderivative is just p to n plus 1 minus p to n minus 1. It's just the integral of a derivative. So let's take out the constants out of the way. 1 over 4m plus 1 comes out. And then the antiderivative, like I said, is p to n plus 1 of x minus p to n minus 1 of x evaluated between 0 and 1. Now, this will be a little bit trivial or unsatisfying if you want, because it's going to be basically 0 with one exception. I'll get to that immediately. So one thing to keep in mind is that, remember, when you have these coefficients, n goes from 0, 1, 2, and so on. So whenever you apply these formulas, you have to recheck whether you have a separate case to be taken separately. That's very important, right? Because remember, the lowest possible index for these polynomials is 0. Now, if the index is 0, 1, 2, and so on, clearly this formula, when you apply it, only works for n from 1, 2, 3, and so on. Because when n is 0, you have p sub minus 1. So the case n equals 0, I need to look at it separately. You might remember that when you dealt with the Fourier cosine series, you had situations like that as well. However, later on, when n is, like I said, for all other cases, when n is 1, 2, 3, and so on, this is actually trivial because, take a look at this, what happens. If I plug in 1 into the Legendre polynomial, I know that the value of the Legendre polynomial of 1 is 1. So when I'm going to plug in 1, it's going to be just 1 minus 1. Then when I plug in 0, odd polynomials evaluated at 0 are equal to 0. So that's also 0 minus 0. So basically all the Legendre polynomials for the for 1, all the Legendre coefficients, sorry, are 0 in the even Legendre polynomials develop expansion for 1. Now, what about n equals 0? Like I said, this case needs to be taken separately. So then I go back to the original formula and I say, okay, I need to compute a naught separately. So when n is 0, that's going to be 4 times 0 plus 1. And here you have to basically replace p naught of x explicitly with its value. P naught of x is just 1. So that's going to be just the integral from 0 to 1 of 1 dx, which is basically 1. Okay, so essentially 1 has a trivial series in terms of even Legendre polynomials. This is not really that surprising because, again, 1 is a non-zero constant. And so then obviously you can have that to be the first coefficient and then the rest of them would be 0. So let's move on and do exactly the same thing now in terms of, like I said, odd polynomials. So let's do the expansion in terms of odd Legendre polynomials. Now, the formula for the coefficients in this case, a to n plus 1, is the integral from 0 to 1. I forgot the coefficient, is 4n plus 3. The integral from 0 to 1, 1 times p to n plus 1 of x dx. Let's write it actually nicely here from the beginning. All right, same thing as before, but again, we have to be careful because it's going to be even more tedious. We're going to have to replace n with 2n plus 1 in that formula. Let's write it again in this corner here. We have the formula that Pn of x is actually 1 over 2n plus 1 p prime n plus 1 of x minus p prime n minus 1 of x dx. Just p n minus prime of x. So I'm going to have to replace n with 2n plus 1 because I have 2n plus 1 here and I have to replace it here and everywhere in the formula. So we have 1 over 2 quantity 2n plus 1 plus another 1. And then p prime 2n plus 1 plus another 1 makes it 2n plus 2. 2n plus 1 minus 1 makes it 2n. So that's really the tedious part on using these formulas. You will have to replace n with 2n, 2n plus 1, 2n minus 1, n minus 1. It all depends on what comes up when you do these integrals. And you have to follow through with that substitution in the formula. And again, have the habit of pulling the constants out to make it a little bit easier. So we have 4n plus 3 times 1 over, this guy is going to be, again, 4n plus 3. And now the antiderivative, p to n plus 2 of x minus p to n of x between 0 and 1. Now notice here I don't have to worry about an exception case. N going from 0 to infinity, 0, 1, 2, 3, all these indexes are well defined. I don't have to take any case separately. So look carefully. When I plug in 1, again, that's going to be 1 minus 1 minus, and when I plug in 0, p to n plus 2 of 0 minus p to n of 0. These are no longer 0 because these are both even polynomials. So the formula for the coefficient is p to n of 0 minus p to n plus 2 of 0. So like I said, if I don't say otherwise, you can leave it like that. If you want to write exactly what they are, these coefficients, now you can apply the formula for p to n of 0. So let's look it up. P to n of 0 was minus 1 to the n to n factorial 2 to the 2n n factorial squared. So I'm going to copy it here for the first term. And for the second one, I'm going to have to replace n with n plus 2n plus 2. Rather, n with n plus 1. You got to be careful here because 2n plus 2, it's like p2 sub n plus 1 of 0. Because you can factor 2. So I have to replace n with n plus 1. So minus 1 to the n plus 1, 2n plus 2 factorial. This will be 2 to the 2n plus 2. And on the bottom, n plus 1 factorial to the power 2. We can simplify this a little bit, but you kind of see why actually most of the time we'll be happy to leave it like that, because it's really tedious and most of the time it's not easy to simplify by hand. I'm going to just do it to have a nice example at least. So you can pull out minus 1 to the n, 2n factorial, 2 to the 2n, n factorial squared. And inside the parentheses, you're left with 1. Now pay attention here, you pull the minus 1 to the n, there's another minus 1 left, with the extra minus sign becomes plus. If 2n factorial is out, the remaining factors left are 2n plus 1, 2n plus 2. If n factorial squared is out, you're left with n plus 1 squared. And 2 to the power 2 here, which is 4. Let's do a little bit more simplification. Let's see. We can pull a 2 out and divide by 4, which is 2. And then it's left n plus 1 that cancels with another n plus 1. So 2 is out, n plus 1 is out, and on the bottom you're left with 2 n plus 1. 2n plus 2. So when everything is said and done, on the top is 2n plus 2, 4n plus 3. And on the bottom, I can combine these two with 2 to the 2n and n factorial squared and another n plus 1 on the outside. Very tedious. Very, I mean, nothing, you don't expect more, compact answers, okay? So 1 as a series, right, from 0 to infinity in terms of odd polynomials will have this expansion. And then p to n plus 1 of x. Okay, so on the last part, we're going to have another short last part for today. I'm going to illustrate how you can use these recurrence formulas to compute series for more complicated functions. But I'm not going to go too far on that one. We're going to go over other examples next time. And in those cases, most of the time, again, like I said, we're going to leave the answer in terms of even polynomials at 0, or in general in terms of polynomials evaluated at a point without actually replacing explicitly what that value is all about. So stay tuned for the last part.